Welcome to the fourth tutorial video for the Johns Hopkins Final Project Walkthrough. Today we're going to talk about the concept exploration stage, which includes an overview of the life cycle, the inputs, the actual phases that take place, and then a brief discussion about the outputs and the next stage. Recall that the systems engineering life cycle is composed of three separate stages: the concept development stage, engineering development stage, and post-development stage. The scope for this project is encompassed within the concept development stage. Within the concept development stage, there are three separate phases: needs analysis, concept exploration, and concept definition. In the previous video, we covered the activities that take place and the products produced by the needs analysis phase. This provided you with a preliminary concept of operations, an initial system architecture, your operational requirements, and perhaps some risks, but most importantly, your system concept and proposal papers. In this video, we're going to focus on the concept exploration phase within the conceptual development stage. We're going to discuss this concept exploration inputs and outputs and the tailored systems engineering process that takes place during concept exploration. When you perform concept exploration, you begin with the inputs just mentioned from needs analysis, as well as the information regarding the system you will be replacing, and enter the systems engineering process. As I stated in my first video, the Systems Engineering Principles and Practice textbook tailors each step of the systems engineering process and gives them unique names throughout each phase. For concept exploration, requirements analysis is called operational requirements analysis. Functional analysis is called performance requirements formulation. Physical definition is called implementation concept exploration, and design validation is called performance requirements validation. The activities for each of these steps are outlined in detail in Chapter 7 of your Systems Engineering Principles and Practice textbook, and I'll be applying each of these to my project. You'll notice that the primary input to this phase are those operational requirements you develop during needs analysis, and the primary output is the performance requirements, otherwise known as your requirements analysis report for your project. So obviously, focus during this phase is on the development of performance requirements for your requirements analysis report. During concept exploration, I will also be refining my concept of operations and my system context diagram as necessary. Throughout, I will continue to demonstrate how to apply each of these steps using CORE. Operational requirements analysis is one of the most important steps during concept exploration. This step will set the stage for developing our performance requirements, and you've done most of the work already during needs analysis. In it, we'll conduct two primary activities. We'll first analyze the operational requirements we just developed during needs analysis and gauge the level of performance required by engaging with potential stakeholders, some of the users, SMEs, and operators, or conduct market research to assess the current state of technology for this performance. You will need to look at the performance of the predecessor system if you're replacing one and understand the thresholds that your system will have to perform to, or gaps that your system will need to fill. As a result of this, you'll need to refine the concept of operations you began in the first phase and update your operational requirements as necessary. A helpful tip for developing operational requirements is to ask yourself why that particular requirement is needed. If the requirement statement itself answers why, then that requirement's ready for decomposition into a set of performance requirements. If the answer is something different than the requirement statement itself, then the answer to why is typically what you're after, and you should refine your operational requirements to reflect that. For example, the requirement the system shall use Wi-Fi to connect to the network, aside from driving implementation, also begs for an answer as to why you need Wi-Fi. The answer to the question is that we want our system to be deployable anywhere within a house or a business without being constrained by being located close to an Ethernet port in the house. Then our requirement becomes the system shall be capable of accessing a network anywhere within the house or business without the need to install additional physical network connections. Of course, we're not describing what the size of the house or the business is, or that the system may be used outside of the house on the front lawn, for instance. But when we refine our concept of operations and start to develop our performance requirements, then we will develop requirements that support these. This is something that I look for when I grade requirements analysis reports that students submit. I look at the higher level of your hierarchies and ask why. If, for example, I see that you're dictating that a particular implementation solution needs to be included in your system, and this inclusion is not answered by why, then I'll request that you refine your operational requirements a bit. This step is very important so that you don't back yourself into a corner and end up either with a system concept that's not feasible or that could have been met by a better solution in the end. Remember that our operational requirements should be rather broad and allow for multiple ways to implement solutions to meet them in the end. If we're replacing or improving a pre-existing system, it will come with its own set of constraints and must be taken into account from the beginning. Compare the performance of the predecessor system against the research you've conducted during needs analysis. Think about how much better your system will need to perform in order to be of value to potential users and to provide a return on investment to the stakeholders. It's important here to understand that it is almost always not necessary to shoot for the moon, for the lack of a better term. What I mean by this is that if we're developing a new small electric vehicle for urban commuters, it's probably not necessary for our vehicle to be able to go 150 miles an hour or to haul 2.5 tons of payload. We will get a bit more into detail with this when we refine our CONOPS. For now, we'll simply gauge how well, at a minimum, our system should perform compared to the predecessor systems or against the limitations of the technology we're attempting to insert. Before we can move on to the next step and start to derive subsystem functions, first we have to gain a more complex understanding of how our system is going to be used, who will use it, and where they will use it, and when. As I discussed in the last video, these questions are answered by the CONOPS. I also provided you with a few references that should help you in developing a good CONOPS, so take some time here and refine your concept of operations, focusing on answering the various types of missions your system will need to conduct. Know how we know that mission has been accomplished, what relationships your system has with other systems or users, what information your system requires in order for it to operate, what information your system will provide to externals, as well as any relationship your system has with existing architectures or constraints that are imposed on your system. Think about not only how your system will be used in its normal day-to-day operation by the typical users, but also think about alternative scenarios, such as degraded operations or outside threats to your system. Record these as risks if you think it necessary, and mitigate these risks by including their solutions or mitigations into your architecture later. It is at this stage that we really start to think about the various modes and states of our system. Primarily, if doing so enhances our ability to better refine and quantify our performance requirements. There's a great lecture presented by Charles Wasson through the developers of Core available on YouTube at this link. If you would like to include modes and states into your system architecture, I highly recommend this lecture. Chapter 19 of the Charles Wasson textbook also discusses these. Charles Wasson also discusses performing the use cases in order to assist in the identification of your modes and states. I was going to supplement this material with a tutorial on use cases. Thankfully, a company that developed a great use case tool called Case Complete did this for me. We learned a little bit about use cases in our system software engineering course. However, if you'd like to become more familiar with performing use cases for your system, check out the Case Complete Learn channel on their website here. They also offer a free 30-day trial use of their use case software, which I took advantage of when I did my project. You're not required to perform these steps for your final projects. However, it will further validate the fidelity of your system as well as demonstrate your knowledge of the more advanced systems engineering concepts that may potentially enhance your final grade. Core allows you to include modes and states as part of your architecture. There are two separate elements of each of these in the database, one for modes and one for states, and here are their relationships. Keep in mind, as Charles Wasson warned in his lecture on phases, modes, and states, when the systems engineer starts to include modes and states into the system architecture, they must complete the entire architecture for each mode and state. This can sometimes double or triple or quadruple the amount of work depending on how different the various states and modes are from the architectural perspective. For your projects, I would recommend including the primary operational state with the various high-level modes. For the sake of time, developing a complete architecture for each of your modes and states is not realistic, but it's important for you to remember that you would need to complete your entire architecture that your system would possess in reality. My concept has only a few various alternatives. However, if your concept has multiple alternatives, you may want to perform an analysis of alternatives based on what you've learned so far. The guidelines for performing an analysis of alternatives can be found in your Systems Engineering Principles and Practice textbook, starting on page 177. This will help you narrow down the list of potential alternatives to something a bit more manageable for your project. I'll be talking about what I did here on a later slide. After we have developed our CONOPS and refined our operational requirements, we may decompose and derive our performance requirements based on what we've discovered so far. During performance requirements formulation, we'll be deriving subsystem functions for the subsystems we identified from needs analysis and then formulating performance parameters around those derived functions. Particular focus and attention should be made to those functions that help you define and enhance or quantify your performance requirements. This requires the operational requirements, predecessor system inputs, and parameters, and those functional elements we identified as higher-level risks that need analysis. It's at this point we want to focus not only on those higher-risk areas for subsystem functions, but identify those high-level functions that our system needs to perform that will help us to quantify and refine our performance requirements. We'll need to conduct analysis on these functions in order to help determine what performance boundaries should be for these functions. To provide an example, for my system, I want to identify how long the refueling process should take from start to finish by observing and analyzing how long it currently takes vehicles to refuel and use this as an overall baseline that my system should strive to perform. Basically, we're going to complete the picture we started during needs analysis, but still remaining at a rather high level in the functional area. A good discussion about the different types of functions, the inputs, the transformative, and output functions can be found at the beginning of the bottom of page 180 in your SCP&P textbook. So if you're improving on an existing design or integrating new technologies into an existing system, the functions performed by the predecessor system should be identified. This will give you a foundation from which you know you must meet at a bare minimum. Unless those functions were issues identified from the predecessor system, and you'll need to incorporate new and improved functionality to replace the old functionality. If you do not perform this step, you may get all the way to the end and present your project for the next stage, engineering development, and not be able to perform the functions that the predecessor was able to perform. Have you ever upgraded a piece of software and found that certain functionalities that were available before are no longer available or no longer work? That's pretty annoying, isn't it? That's most likely because the systems engineer neglected to include all the functions that the predecessor software performed. For my project, here are just a few primary functions that my system needs to inherit. Accepting various payment types, providing 3 different fuel types, pay at the pump for a car wash service, providing fuel to double-axle vehicles, operating in harsh conditions, allowing the user to accept or reject a receipt, providing the pricing information for each fuel type or ease of maintenance, allowing for the attendant to control the pump, and so on. You could read these for yourself. So for these 4 functions over here, these are also risks. For these 2, we are to assume that the user will stay in their vehicle with their window rolled up during the fueling operation. After talking with potential users, these risks have a very low consequence, so I accept them. This third risk for refueling a motorcycle seems a little silly. However, it is a function that was performed by the predecessor system that my system, as it stands now, cannot perform. People that are riding motorcycles are not likely to be all that interested in an automated gas pump for refueling. I ride one myself, and I know. In extreme weather conditions, they would not be riding their motorcycle, and even if they were, they would probably not be concerned about refueling their vehicle, and would be more concerned about getting home or seeking shelter. So the consequence for this risk is also extremely low and is therefore accepted. Now this function at the top, provide fuel to double-axle vehicles, needs to be defined a little better. I need to define the various vehicle types and decompose this function to address each of these types. For instance, we could have something as small as a smart car to a Honda Accord to a 2-ton pickup truck. This is actually a 1.5-ton pickup truck. All the way to a large moving vehicle. My system should be capable of refueling each of these types. This is also a risk. Assuming that I have down-selected to the robot arm, another risk of my system will run into are the vehicles that have refueling ports behind their license plates, or in the back of the vehicles, or otherwise in atypical locations. I probably should do a little bit more analysis if this solution is chosen to try to evaluate whether or not it's worth leaving alone or accepting, or trying to mitigate it through some design features. In the end, I chose this path and briefed that this requirement can be passed on to another increment, since the primary purpose for increment 1 will be to prove out the concept from both a technical and a return on investment perspective. Spending a lot of extra time and hypothetical money on making the system solve even more complex problems than necessary increases the technical risk and lowers my return on investment. Something that should also be mentioned while I'm here: how do I integrate these into my project? Since these are features and functions of the predecessor system that we want to retain, except for those risks I just talked about, then each of these functions is actually going to become a requirement. So in core, we simply write each of these functions as requirements. For example, the system shall provide from 1 to 3 user-selectable fuel types. Turns into the system shall be capable of dispensing up to 3 different fuel types selectable by the user, and it becomes a requirement in the requirements section. So the question may arise as to how deep you think you should go. I think a basic tip here is to derive functions until you can formulate performance parameters around each subsystem, and each requirement can be verified on an individual basis. Your system should only contain subsystems at this point, and not components. We're trying to calculate how well, in the various ways each of the subsystems should be able to perform. It's important to keep in mind during concept exploration, just as in needs analysis, not to write requirements for physical solutions, unless those physical solutions are constraints to your system. For example, if your system must integrate into an already existing architecture that the predecessor was interfacing with, then those integration interfaces must be taken into account and turned into requirements. For my gas pump project, it's easier for my system to operate on the pre-existing gas pump islands, those concrete islands, at gas stations, than it is to require a gas station owner to build a unique facility to accommodate for my system. Therefore, my system must adapt to these gas station islands to include mounting provisions, the physical footprint, interface with the underground gas tanks, and interface with the network and power provided by these gas stations. On top of complying with industry standards such as UL 87, I discovered these during my concept of operations development. Another unrelated example of a physical solution as a constraint to our system is simply the usage of 120 volt household power in the United States or 220 volt in Europe as standard interfaces. Remember, during performance requirements formulation, we need to identify what the system needs to do and how well the system should do it. This is not to say that we should not be thinking about potential solutions that could meet the requirements. Here, we see that we should be visualizing components for our system at this point and defining requirements to ensure feasibility for the subsystems. To be clear, this does not mean that we should be writing requirements outlining what components our system should contain. Merely be thinking about how, in the real world, these requirements might be met by either existing technologies or feasible technologies that may require some research and development. We did this throughout needs analysis previously as well. Here we're peeling the next layer of the onion and taking it a little bit deeper. Take a look at the operational requirements and the functions that your subsystem will have to perform and decompose them into quantified, measurable, testable requirement statements into this description field in core. Here's an example of how I decomposed one of my requirements for my system. My operational level requirements state in general terms what my system should be capable of doing, usually at a high level. In that description, it refers to an appendix that defines terms used to describe my system. Of course, I could have simply included the definition of this requirement statement, but I wanted to keep it short and simple. Oftentimes, trying to define things in detail, especially at high levels, end up confusing stakeholders that attempt to read your requirements documents. So the appendix breaks down what is meant by extreme weather and any other terms that require some definition for my system. In core, there's a dedicated area for you to put these definitions if you desire. So I take each of these different extreme weather conditions and create performance requirements for each. For example, here I have operating in a hot climate broken down and quantified so as to be testable at an individual level. The other type of requirement, the derived requirement, takes a little different of an approach. My decomposed requirements are simply a closer look at the various items outlined in the higher level parent requirement. Derived requirements typically take a little bit more analysis in order to properly define and break them down into individual testable requirements. For example, this higher level SAFe operation requirement. Here I most likely need to refer to an industry standard for building safety measures into my system that interact with people, such as a gas pump or an automated robot arm, and insert these standards as requirements for my system, taking into account the operational environments and scenarios described in my CONOPS. What I'm going to do with the SAFe operation requirement is derive some lower level requirements that help me to define what I mean by SAFe operation in the context of my system. An example of this would be the inclusion of probabilities for pinching, the ability to detect the presence of moving objects, and so on. With a little bit of thought, you can see how deriving requirements is a little bit more difficult than simple decomposition. It requires a lot more analysis and thought, and it's incredibly easy to leave things out. This is why it's important to refer to standards that have already been developed and analysis that may have already been conducted. Often, students will simply refer to either an industry or military standard and leave it at the high level for their projects for the sake of time, which is a fine approach, but I would recommend at least taking a look at the standards to ensure that it does not call for specific functionality or physical implementations that must be put into your requirements in order to comply with them, as these may impact the overall feasibility of your system. And remember, one of the primary purposes of concept development is to demonstrate that your system is feasible. If it does call for the inclusion of specific functionality or components, those must be included in your system as constraint requirements. For my system, after looking at the industry standard for gas dispensers, which is UL87, an example of this would be the placement of an emergency fuel shutoff button in the immediate vicinity of the gas pump. Since the user's inside their vehicle, the placement of this button will obviously be influenced by this. You will also be identifying what your key performance parameters are for your system. You do this in Core by selecting KPP from the category dropdown in the Requirements Properties sheet. It's very important that you understand the definition of what a KPP is and to properly identify KPPs for your system. I'll help you and give you the definition of a KPP from this Test and Evaluation Management Guide. Those capabilities or characteristics so significant that failure to meet the threshold can cause for the concept or system selected to be re-evaluated or the program to be reassessed or terminated. Now, most of the students working on their projects have had real-world experience with KPPs, whether they've been called KPPs or some other naming convention was used, and most students know that if a KPP cannot be met, well, that's okay. It's not really the end of the world. What are we going to do, not buy the multi-million-dollar aircraft? Cancel all the contracts and start all the way over and go back 10 years? Not having something to replace the predecessor as promised in the schedule? And if we start over, what's the guarantee that the next person will meet the KPPs as well? No, we're going to accept that the KPP wasn't met, likely at some executive level, and press on. So what I just described is not the systems engineer's perspective. That's the program manager's perspective. The systems engineer's perspective is that the system is not worth developing, producing, deploying, and sustaining if all the KPPs cannot be met. Now think about that. If certain requirements are absolutely necessary to declare your system a success, what kind of parameters are you going to put around it? Should it even be a KPP? These are very important questions to answer for KPPs, as they have very high dollar consequences if improperly chosen. The systems engineer does not accept that the KPP cannot be met. For my system, there are a few KPPs. Obviously, the ability to autonomously refuel vehicles is a KPP. I did not include the legacy timeline for this, however, primarily because for many users, waiting a little bit longer than it would take for the legacy system would not render my system completely useless. It would still provide some value. Some other KPPs include refueling without scratching or damaging the vehicles. Another one was the ability to recover from faults while refueling. Nothing would be worse for a user if the system broke while the nozzle was stuck in their vehicle. A fourth KPP for my system, as we touched in the previous slide, is that my system needs to be safe for use with what are obviously hazardous materials. This particular one can be decomposed a bit more in order to make it quantifiable and testable. However, keep in mind that if a parent-level requirement is a KPP, then that's the same as saying that the amalgam of all of its children are also KPPs. In other words, if all of the children cannot be met, then the parent cannot be met, and therefore the system is not worth developing. So be very careful here when you decompose or derive these requirements down into lower levels. Let's get back to talking about writing your requirements. Some good references are your Intro to Systems Engineering and System Integration and Design slides, or System Design and Integration. I can't remember off the top of my head. Some other good sources are the section 7.2 in your SEP&P book, 6.9 in Dennis Beatty, and chapter 28 through 33 in Charles Wasson's. This is the area where you will and should be able to shine, as a strong set of requirements typically is what makes or breaks the development of a system. Spend a lot of time here and ensure that you're doing it right, if not for the sake of your project, then for the sake of your professional careers. This is probably the most valuable skill you can possess as a systems engineer, and having this skill mastered will put you in great demand. You may need to bounce back and forth between your operational requirements and functions to refine them in order for you to properly answer those questions of what, how, where, and how much, etc. You may find that what you originally wrote as an operational requirement or a function could be better stated after you've attempted to decompose and refine this into a quantitative performance requirement. This is a very important part of the performance requirements formulation step. If you would like additional material for ensuring that your requirements are sound, the Department of Homeland Security has a very robust guide for developing operational requirements. You'll find this in the Intro to Systems Engineering Module 3, or you can search for it on the internet. There's also a series of slides by Nkosi provided at this link. After we're comfortable with formulating our initial performance requirements, we can proceed into implementation of concept exploration. It's here that we identify the physical elements of predecessor systems that our system is going to be incorporated with. What kind of physical interfacing our system is going to have to comply with in order to work with the predecessor system. Will it replace the entire system or only part of it? It's here that we identify those physical interfaces that our system must take into account from the beginning. For example, if we're replacing the reciprocating motor in a vehicle with a new hybrid half-reciprocating, half-electric motor, the vehicle's chassis and mounts, the fuel system, the drive system, etc. should continue to interface with our new upgraded motor. We're not planning on replacing any other major subsystems in the vehicle, only the motor. So we have to design our motor to adapt to the old motor's interfaces. If we're implementing a new piece of advanced technology, we must take into account the various design alternatives to meet our requirements with the mission scenarios we describe in our concept of operations. If our new technology has only been proven in lab environments, we must take that into account and plan on full integration in order to meet operational requirements. For my project, I eliminated 2 of the options based on physical implementation considerations. From a cost and practicality perspective, as well as non-compliance with UL 87 standard, the garage implementation is eliminated. There would simply be too much hardware as well as an entire facility to build at every gas station I wanted to install my system at. My second option, with the refueling probe being inserted into the vehicle from underneath, was eliminated because it's not feasible, since every vehicle that wanted to use my system would have to install a special connection on the underside of the gas tank. This brings with it a slew of vehicle fuel tank design qualifications, as well as the added cost to the potential customers. For your projects as well, not only must these potential implementation options be analyzed against the requirements you've developed so far, but you must consider the entire system lifecycle, from development and test through production and into fielding, sustainment, and upgrades. Considerations such as training, packaging, handling, storage and transportation, supply support, ease of maintenance, transportation, setting up and tearing down your system, special equipment needed to use it, and disposal of your system must all be considered. Now we need to consider performance requirements validation, the last step in the systems engineering process during concept exploration. Here we need to validate our performance requirements we've derived and developed from our operational requirements and convert them into our requirements analysis report. The 3 questions that must be asked for validation for each of these requirements is, do they define what the system must do and how well it must do it? Do each of your performance requirements define those characteristics and engineering terminology that can be verified by analysis, demonstration, test, or inspection? Have you completely captured and decomposed or derived all of your operational requirements and constraints, including all those interfaces with external systems, such that they're all realistically testable at an individual basis. Another piece of validation is the traceability from your derived and decomposed performance requirements up to your operational requirements, and ultimately up to your initial need statement. This is easiest accomplished in the Traceability Matrix that I touched on in the previous video. Traceability for your requirements should have the type of structure shown here. For your requirements analysis report, it's not necessary to report the relationship between your requirements and your functions, or your functions to your subsystems. That will be shown in your functional analysis and conceptual design reports. The purpose of performing functional analysis and physical allocation during concept exploration was for you to refine your requirements and develop your initial set of performance requirements. Notice also that the lower level requirements are refining higher level operational requirements, and not the need statement itself. It's not necessary to duplicate the relationships to even higher level elements, as this is implied by the relationship with the elements in the middle of the relationship. This becomes especially important when your architecture begins to evolve and change, as you only need to keep track of a single relationship if you do decide to change things. Here's how the traceability might look at this point in your project using Core. So here we've got my final project in Core. This project is complete, so you kind of have to ignore the fact that I have all of the functional analysis and the physical allocation complete for this for the moment. I'm just going to show you traceability in Core. So for the requirements traceability, which is what you're concerned about during concept exploration, is you want to basically show that all of your requirements are traced from the top down and back again from the bottom up. So forward traceability and backward traceability throughout your requirements. Traceability to functions and components is not required until concept definition, which is the next stage. So what we're going to focus on right now is taking a look at traceability forwards and traceability backwards. The way to show that is select the top level requirement that you have for your system. And this looks a little different from what I had in the video just because this is my actual project from 2008 when I did it. And there are some things that I changed in the videos compared to when I did this project. So just keep that in mind. So with that selected, what I did was I clicked on this little table button up here, show elements and their attributes and relationships in a tabular format. And this shows that. I gave you a little introductory to that in, I think, the second video. And what we're looking at right now is a top-down traceability from the requirements here. So we've got the number of the requirement, and we can change the size and shape of these. The name of the requirement, the description of it if we want the description, what type of requirement it is, the origin, and so on. Here's the basis of, and this shows the forward traceability to functions. We're not concerned about that during your requirements analysis. Report writing period, so don't worry about that now. What we are concerned about is this refine by. This is what we want to show as the children requirements, the forward traceability from the parents to the children. And then we have this specified right here. This is basically constraint requirements that are specifying specific physical or functional configurations. So what I'm going to do is tailor this a little bit, and you do that by right-clicking up here and editing the columns. And we could take out anything we want to in this table. What we're going to show is we're going to take out basis of, and we're going to take out specifies, and we're going to put refines in there. So I'm just double-clicking on these. So now we've got refines and refined by. I want refines to be before refined by, so you go over here to this arrow and click up on it. And I also want to take the description out. I don't need the description on the traceability matrix. So I'm going to do that, but this is basically what I expect to see. And what you're going to look for in the traceability matrix, in your requirements traceability matrix, is you're going to be looking for, if it's a parent level requirement like these guys up here, you want to see that it's refined by requirements and take a look at the titles of them to make sure that it makes sense. And if it's a child requirement, such as all these little guys down here, we want to make sure they refine something over in this column. What you don't want to see is a requirement that's blank that has nothing in either one of those fields. So you got to go through all of your requirements and make sure that you don't have that. And mine's pretty consistent right here. And I have my requirements bucketed into the general system requirements, my customer interface subsystem that I identified during needs analysis, and the vehicle interface subsystem that I identified also during needs analysis. So that's the gist of traceability. You can also choose any of the other fields in here. So one of the other ones, and I didn't do this with this project, but I'll do it right now, is I talked about just a few minutes ago that verification. So if we go in here in verification requirement, let's fill those out real quick. And what we can do once we have these created is we can go back here to the requirements, and this is how we show our verified by. So we click on verified by. Primary one will probably be verified by all four. So I'll just click that just for demonstration purposes. Refueling. I'll just go through here and assign these. In fact, I'm going to pause the video and do this. Okay, so I've gone through and I actually went through, I just clicked on each one of the four elements. It was easier for me to do this. I just double clicked like on test, and then double clicked on verifies, and then I just selected from the list of all the requirements, and I only chose, just for demonstration purposes, my first folder here with my primary requirements. Chose those requirements that are applicable to that. Selected those and included those in here. So I'm going to go to the traceability matrix again, and then I'm going to add the, let's click on the top level requirements here. So I'm going to add the column, the verified by column in here, edit columns, go to the bottom here, verified by. Hit OK, and there we have the verified by method shown here. Unfortunately, you can't hide that verification requirement word right there, so you have to bear with the fact that it's a little bit wider than you'd normally expect, and that's okay. So this is basically what your traceability is going to look like for your requirements analysis report. Now the way we get this in our requirements analysis report, and I showed this in my first set of videos for how to use Core. All you got to do is click on this upper left corner, this box that doesn't say anything in the upper left hand corner. Click on it and it turns everything black. Then right click and click on copy, and then go into Microsoft Excel and select the first cell in Excel, and then hit paste, and then everything will populate in Microsoft Excel, and you can export your Excel file into your requirements analysis report. So that brings up another good question. How do you export your requirement elements into a document for your requirements analysis report? Well, let me show you how to do that real quick. What you're going to do is go up here into the upper left hand corner, and this third icon right here in the middle, actually it's the fourth one, it has a little W on there, like a little Microsoft Word looking thing with the database symbol behind it. So what we're going to do is click on that. It's run a script. Then we're going to choose the script type drop down right here. The script type we're going to choose is right here, System Description Document version 2.5. Then we're going to get OK. Run it with the primary component. I'm going to say no. And then you choose what you want to see. I'm not going to choose a cover page or table of contents or those things, because I'm going to go back in and add introductory paragraphs and so on with some additional verbiage, so it's going to be in my own format in Microsoft Word, so I don't need those things in there. Don't need components overview for requirements. What I do need are originating requirements, design constraints, performance requirements, any concerns and decisions I had or risks if I want to include those. And then we get into the functional behavior model. We don't need any of those. Use cases, components, interfaces. And let's try, I don't think Traceability Matrix works for this one, but we'll try it. And if you have anything in the glossary or acronyms, part of the database, it'll include those too. But I don't, so I'm not going to add them. So then I'm going to hit OK. Any diagrams, we want the hierarchy diagram and the requirements diagram. And then choose a place to upload it. So I'm going to choose this one. You can name it whatever you want to. I'm going to just keep it at that for now. And then you might get this potential error right here. And that's because these requirements right here are actually functional requirements. So what you have to do to actually get them to export is go back into Core and rename them as something other than functional requirements. It's just a knit with Core. So go in there and name them something other than functional requirements, and then you should be able to export them. So once it finishes exporting, it's going to save into the folder that I just saved it into, and it'll be a rich text format, RTF format. So what you'll do is you'll open it in Microsoft Word, and you can edit it in Word. And I would recommend saving it in a docx format because it compresses the pictures and makes the file size a lot smaller. If you'd like to increase your likelihood of getting an A on the project, You may take this time to write verification requirements into core for some or all of your performance requirements. In core, here's how the various tests-related elements are linked together. Obviously, there's quite a few elements and relationships to establish for each requirement. That's because core was developed for use during the next stage in the system lifecycle, when your organization's actually preparing for and running actual tests. For conceptual development, we need to merely identify the verification method. I will tell you that it's rare for students to do this, and your grade will not suffer if you don't do this. However, your verification methods must be identified in your requirements analysis report. This is done in core as one of the attributes of the verification requirement. However, I feel it's much easier to kind of cheat a little bit and use core in a way that it was not intended. If you'd like to keep everything in core, just create 4 new verification requirements, 1 for each test method, and link all your requirements to one or more of these via verified by relationship. Keep in mind that this is not practical in the real world, since you'll use this same architecture and these same elements to begin the next phase of development, and you don't want to be messing your architecture up by dual-purposing verification requirement elements. Refer to your project guidelines for how to properly format and present the requirements analysis report for your mentor. Remember in the second video I gave you a tip to make a bulletized list of what is required in your requirements analysis report from the project guidelines, and check the box, so to speak, next to each bullet as they are met in your requirements analysis report. Some additional great tips and pointers have also been provided in Steve Biemer's office hours. I would also highly recommend updating your risks as you have identified them up to this point in your risk analysis report. Oftentimes, a risk mitigation will help guide the systems engineering process by leading you down a particular path that contains less risk, or will help you choose functional architectures or physical solutions that contain less risk than they would have had you not been tracking your risks throughout the system concept development. Here's the path to Steve Biemer's office hours once again. Once you're confident that your requirements analysis report is ready for review, submit the document in the 800 site. Once you're confident that your requirements analysis report is ready for review, submit the documents in the 800 site. At this point, you may wait for your mentor to review and provide comments, or you can press ahead at risk and begin the concept definition phase. Based on my own personal experience, the risk that you will have to go back and change significant areas of your requirements report is typically small enough that you may want to just go ahead and press ahead while you're waiting for your mentor's feedback. Ask your own individual mentor if this is what they would prefer. Let's visit the concept exploration phase one more time and talk about the 3 outputs. The first is the loop back to the operational requirements analysis. This is the check from the validation step to ensure you've properly captured your objectives and flowed them through the process to arrive at a testable, quantitative performance requirements. The other output is the candidate system concept, or concepts. Almost every student has down-selected to a single concept at this point. However, in the real world, it's not unheard of to develop separate concepts in parallel and compare those capabilities of the solutions at the end, and then choose a solution to advance into the engineering development stage. The third output is your approved set of system performance requirements. These will be used to form the foundation for your functional analysis report and concept design report in the next phase that takes place. So you've just performed concept exploration, and it's now time to really get into the project for the rest of your deliverables in the concept definition phase. Let's get going.